How about now? Okay. The normal force is perpendicular to the surface. So always makes a 90 degree. That's what perpendicular means. You're at 90 degree angle. And we give it the letter N. We use N for normal force. When you see N with the arrow over it, that's not a Newton. That's a force. That's a normal force. When you put your book on a desk there, this is your book. Your book has a weight, which is mass times gravity. So if your book is 5 kilogram, 5 times 9.8, that's 49 Newton. Newton's third law says for every action there's an equal and opposite reaction. That means that desk is going to push back on your book upward. And that's your normal force, perpendicular. This is the table here. So now the table is pushing upward of how big that force? What's that normal force should equal to? Has to be 49 Newton. Why? Because in Newton's second law, if this force was larger than this, what will happen to that book? Elevate, it will rise. If this was larger than that, if the net force is not zero, this will go through the table. So the fact the book never moved, just took the book, here's my book, put it on the desk and sat there. It didn't move. That means the net force in this direction is zero. But that's your normal force, N. It's always perpendicular to the surface. And it's equal to the weight. Is the normal force always equal to the weight? The answer is no. Why not? Let's go back to that suitcase. Go into the airport. You get the weight of the bag down. We'll say it's 10 kilogram. If I remember, we did that 10 kilogram, right? That suitcase has a weight equals 10 mass times gravity. 10 times 9.8, which is what? 98 Newton. It's pushing on the floor. So we'll use JFK, John F. Kennedy International Airport, New York. So that suitcase is pushing on the floor of the JFK Airport. Well, what is the airport doing to that bag? It's pushing upward with the value of N. Now, if nobody's touching the bag, if there's nobody's there holding the bag, doing anything to it, what do we know about these two forces? They're equal. But let's change the story a little bit there. Now they said, next customer please, and you drag your bag behind you. You want to get your boarding pass. This is a 10 kilogram. This is the weight, which is 98 Newton. This is the ground pushing up, the normal force. Doesn't matter if I put it on the bottom, the top, it doesn't really matter. It's pushing upward. And you start pulling your bag behind you. What do we use? We used 20 Newton last time, right? What was the angle? I remember doing this example. What was the angle we pulled with? 30 degrees? Or 15 degrees? Right? 15. So that angle here is 15. So we can take that force here and break it down to x and y component. So if I do that, it will look something like this. I have the weight down. The normal force pushing upward. I'm going to have two values, one in this direction and one in that direction. In this direction is what? 20 cosine 15. In this direction what? 20 sine of 15. The 20 sine 15 is 5.2. And the 20 cosine of 15, I think, if I remember, that was 19.3. Now, you were pulling the suitcase behind you. Was the suitcase moving up and down or just dragging on the floor? The suitcase was only moving this direction. That's the only direction that moved. It moved in that direction. What does that mean about the y direction? That must, the acceleration, it didn't move. The acceleration is 0. If the acceleration is 0, it says the net force should equal mass times acceleration. Well, there is no acceleration. There is no even movement in the y direction. That's a 0. And for the net force to be 0, that means if you take all your forces that are pointing upward, if you add them all, that means summation should equal all the forces pointing down. It has to be. If the net force is 0, that means all the ones pointing up, all the ones pointing down should be the same. So what do we have pointing upward? We have the normal force N plus what? The 5.2. And what do we have pointing down? The 98. What is N equal to? 92.8. It's less than the normal weight. Which means if I want to move this desk across the floor, it's easier on me if I pull up, like I pull and bring it in, instead of pushing down. Why? What happens when you push down on it, when you move that desk? And you're pushing down instead of lifting up, instead of pulling in that direction. So let's take the same suitcase now and show you what will happen if you decide, you know what? The suitcase doesn't have an arm to pull on it, so I'm going to push on it. This is the 10 kilogram suitcase. Has a weight equals 98. Has a normal force, which we're not sure what that is. But instead of pulling on the suitcase, you pushed on it. You were behind it, pushing on it. That angle was 15, right? I'll give you the same angle. That's 15. And the value was 20 Newton, no change. The only difference, instead of pulling, you lean over it, push down on it. What is my normal force? What is that going to equal to? That's what I'm looking for. Again, let's look at my forces. There's my 10 kilogram bag. I get the weight down. I get the normal force up. Now this force, notice is going to go from here to there, you have to go to the right and go down. Right and down. So it's going to have a component in this direction of 20 cosine the 15. And it's going to have a component in this direction of what? 20 sine of 15. If you use 20 sine negative 15, it tells you it's negative, which means pushing down. So I didn't put negative because I just drew it pushing down. You can't make it pointing down, put a negative value. That's double negative. It's one or the other. So you can make it, I'm going to make it pointing upward with a negative number, fine. Or I can make it pointing down. I know it's down. That's what the minus sign tells me. So but the value of that is this number. So this is 5.3 down. I didn't put negative. I made the arrow pointing down. This is 98. This is what? 19 point, what was that number? 3?
I think the other one was 5.2.
2? Oh, thank you. And again, the suitcase was just going on the floor. It was moving that direction. That means in the y direction, these vectors, the net force must be 0. In the y direction. I use y for the y direction. That means if you take all the forces pointing upward, should equal all the forces pointing down. So what do we have now? What's pointing upward? It looks like only the normal force, right? And what is pointing down? The 98 plus the 5.2. What happened to that normal force? 103.2 increased. And you're probably going, who cares about the normal force? I don't care if the ground pushes up or not. Well, you will learn next class that the friction force actually depends on the normal. The larger the normal force, the more friction that you have. The less friction force, the less the normal is, the less the friction force. The reason when you push on that table is not going is the friction. So if you can reduce the friction, it doesn't take much to move it. Yes?
If we're in the homework, just for like labeling the normal force, do we just put an N or do we need to put the little?
Our book is using N for the, you want to put the arrow on it, that's a normal vector.
Right.
To indicate that, you can, yeah.
If it like asks for the units on the homework.
The unit would be Newton for that. So when you write the unit, you go N, but don't put a line over it.
Right, okay.
That's the reason that they used Newton. Sir Isaac Newton, the one came up with the 3 laws. To give him credit, they use N. So this is just the unit. Okay. That's not a vector, but this is the vector. And we know in this case it's actually really pointing upward if you want to indicate the direction of it. The normal force here is upward.
Put a capital or will it take a lowercase?
I'm looking, actually, I was looking at our book. All the normal force, they use in capital N for them. Okay. Just in their diagrams. Now remember what I said earlier about the normal force, always perpendicular. So if you have a car sliding, going down like the road like this, this is the car. It's moving this way. Which way the normal force then is going to be? Yep. The normal force should be pointing upward, perpendicular to the surface. It will be in that direction. So if the road makes like a 10-degree angle, you have a steep, that's by the way a steep road, doesn't seem a lot, 10 degrees. Let's say the road makes 10 degree with this line, with the horizontal. There's a little incline or decline. Depends if you're going up or down.
What is it? Normal force is perpendicular
to the surface. Yes. I think where was that here? Right here, Jackie. Normal force is perpendicular to a surface, always. And the weight doesn't matter. The weight's always straight down, like this. That's the weight. So if you put the car there and you forget to put your brakes there, let's neglect friction. Well, if you neglect friction, it doesn't really matter if you put your emergency brake on or not. It won't make a difference. If there's no friction, what's going to happen to that car? Coming down. Why? The weight of the car. What does the weight of the car going to do to it? Well, if you look at that, I'll just make a dot. The car is a dot now. There's the car. You get the normal force go in that direction. We get the weight, which is straight down. And let's say this angle is what? 10 degrees? We said 10. Can you take the weight, which is mass times gravity, and break it down? Why would the car come down? Because if you make this your y-axis, here we go, I'm going to use a red color for this. This is my y-axis. This is y-axis. And make this my x-axis. Can you see the two vectors? If this is 10 degrees, what's this angle, by the way? Here's your geometry.
80? Well, 170.
Try again.
260.
How about 10 degrees? Why? This is 90 degrees right here, right? When you add all the angles in a triangle, what's the sum should be? 180. You have 90 plus 10, that's 100. So this is 80 degrees. My picture is deceiving. If this is 80, what's the whole, each quadrant is what? 90 degrees. So this has to be 10 degrees. So if you want to draw that normally now, go, wait a minute, I don't like them being crooked like this. I can't think that way. I'm one of the people. So when I say that, I'm actually guilty. My imagination is horrible. So this is the y-axis. This is the x-axis. If I take this now, redraw that one, I get the normal force upward. And I get the weight down this way. And this is 10 degrees. Now, keep in mind, this is 10 degrees. Can you find the x and y component for that vector? This is the weight here. So if you want to break it down, you need to go down this way and go to the left. It's going to have a component in this direction and a component in that direction. So what are these components then? Will be. Now you got to change a little bit your thinking about trig. We always said the x value is always the cosine, the y value is the sine, right? Well, I'm going to tell you, well, not today, not now. So this is the y-axis right here. This is the x-axis. When you break this one into two values, to go from here to there, you have to go down and go to the left. So I know both going to be negative. It's going to have a component in this direction. It's also going to have a component in that direction. And what are these pieces? This is mg, what? Cosine of 10 degrees. And this is mg, sine of 10 degrees. Why is the x value using the sine and the y value using the cosine? We've been saying for the past, what, 3-4 classes, that the x value is always the cosine, the x component, the y value is the sine, right? Why suddenly I'm changing that? All the previous examples that we gave you, the angle was given with respect to which axes? X. And now the angle with respect to which axes? The y. That's why we're changing these. Because this is really the adjacent. The y value now is the adjacent, and that's why it's the cosine. And the x value, that component in this direction, it's the opposite to that angle, and that's why it's the sine.
So how will you know when to?
So anytime you have a problem like this, incline, they give you that angle, this value is always mg sine, cosine, this value is mg sine. You know? Mg sine, mg cosine.
So anytime is in anything?
Yep. So now if I said to you we have a car, I'll give you An example, climbing a hill there, or sliding down the hill, or a skier coming down. I'll use a skier. We have a skier, downhill skier, has a mass as the skier. The mass of the person is 90 kilogram, close to about 190 pounds. Neglect friction. If you neglect the friction, we can always put the friction, but that's a whole chapter coming by itself, so I'll neglect it for today. In the next chapter, friction comes in, so no friction yet. Tomorrow we'll have friction. Then this person is going to have the weight down, which is mg, the weight, and the normal force upward if there's no friction. That's all the forces. Let's give an angle. This is a steep slope. Let's go to Colorado skiing. The mountains are nice there. Let's say this angle is 30 degrees. Again, if you want to make this your y-axis, if this is, you want to make this your y-axis, and this is your x-axis, you can. That's why I do always with these problems. Then if this is 30 degrees, this angle is also 30 degrees. So now if we draw that one, here we go. I'll put my y and x axes right there. Here's the normal force pushing upward. I'm going to take the weight and break it down to two parts. One this way and one this way. To go from here to there, you have to go down this way and come back this way. This piece here, the one along this line, that's this one, it's mg sine of theta. And this piece always mg cosine theta. The mass is what? 90 times 9.8 times the sine of 30 degrees. This number is 441 Newton, and mg cosine 90 times 9.8 times what? The cosine of 30 degrees. This one is 764. Now think about that skier. When the skier is coming down, just sliding down that slope there, is he going up and down this way? Is he moving that direction? Not really. That says that the normal force has to equal to what? mg cosine theta. These two have to equal to each other. Otherwise, if this was heavier, the skier will sink into the snow. If this is bigger than this, you'll see the skier rising up in the air. The fact that one moves, so the normal force will be, in this case, is equal to 764 Newton. Again, why am I interested in the normal force? Because that's the force, or that's the value I need to use to calculate the friction force. You will see in next class when we bring in friction, I'll say the friction force equals some coefficient of friction times the normal force. So I need to know what the normal force is. The bigger that number, the more friction force you're going to have. The smaller the normal force, the less friction you're going to have. Again, in some cases, you want some friction. In others, you don't want any friction. If you're a skier, if it's Lindsey Vonn, Lindsay skiing, she wants to be as fast as possible. She doesn't want any friction. If you're competing for the World Cup or Olympics gold medal, you want to be flying with no friction anywhere on your body, between the skis, your body, and everything. That's what we spend millions of dollars researching. How do we minimize the friction so she can be the first one to win the gold medal? The other side of it, if it's a car you're driving and you want to climb that hill, that's your driveway, you better have a lot of friction. Otherwise, that car is not making it anywhere. So there are cases you want to have some friction. There are cases you don't want to have some friction.